Okay, so we have question 5. It says a block of mass m slides down a frictionless slope to point B, and then at point A, which is 0.7 meter above the ground, the speed of the block is 2 meters per second as shown in the diagram below. Now 5.1 says use the law of conservation of mechanical energy to calculate the speed of the block at point B. So as we can see here, the block is moving from A all the way to B. Now we want to use the law of conservation of mechanical energy. Let's go. We have sum of mechanical energy at A is equals to sum of mechanical energy at B, right? Now we know that mechanical energy is the sum of the object's kinetic energy and potential energy. Therefore, we have half mv initially squared plus mg h initially, then is equals to half mv finally squared plus mg h finally. Now let's come to substituting. That means now we have half, and then our mass is m, then the velocity initially at that point is 2, and then square plus, what is my mass? It's m, and then g is 9.8. Then the height initially at that point, the height was 0.7, is equals to half, my mass is m, and then the velocity finally, that's what we are looking for at point B, right? Then plus the mass is m, and then we have 9.8, but the height finally there at point B is 0 because there is no relative height. Then here we have 2m plus 6.86 m is equals to 0.5 m vf squared. So if we just take this half as 0.5, and then this will just be 0 because we are multiplying with 0. Now if we add this, we have 8.86 m is equals to 0.5 m vf squared. Now at this point, we can just divide both sides by 0.5 m. 0.5 m. Now at this point, this will cancel and also the m's will cancel. So we have vf squared is equals to 17.72. But we are not looking for vf squared, we are looking for vf. So we can square both sides, and vf we have 4.21 meters per second. That's how you have it. Now the statement below that says the block moved from point B to point D on a rough horizontal surface. The kinetic frictional force between the block and the rough surface is 3 Newton. The block reaches point C with a momentum of 5.79 kilograms meters per second to the left and kinetic energy of 11.17 joules. Now 5.2 for 3 marks says calculate the speed of the block at point C. Now what are we given? We are given the momentum and we are also given the kinetic energy. Now if we can look at these two formulas, let's see the relationship between these two formulas. We have EK is equals to half mv squared, and then we have momentum is equals to P m times v, right? So the momentum here we are given that it is 5.79 kg meters per second, right? So that's our P, and we are also given EK is equals to 11.17. Now if you can come here, this is EK, and break down this formula here, you have half m, and then that's v times v. Now if you can check here, you can see that this here in between represents the momentum. Remember, momentum is mass times the velocity, and in this equation here we can see that we have mass times velocity. That means we can just substitute this 5.79 into this because this represents the momentum. So we can now rearrange this formula to be the same as half PV, like that. So now we have EK is equals to 11.17. And then what is our momentum? Our momentum is 5.79. And then here we have V. So if you solve this, this is 11.17. Then punch this in your calculator. It gives you 2.895. And then here we have V. So we can just divide both sides now by 2.895. Also this side, 2.895. Then our V is 3.86 meters per second. Awesome. Now 5.3, we have, it says state the work energy theorem in words, right? So let's run quickly to that. Work energy theorem states that the net work done on an object is equal to the object's change in kinetic energy. Now 5.4 says use energy principles only to calculate the distance x. But what did they say here? They say the block comes to rest at point D at distance x from point C. So remember, we have already calculated the velocity at point C, which was 3.86 meters per second. Now we are told that at D it comes to a stop. So what is the velocity there at D? That means it's 0, right? It comes to rest. Rest means it comes to a stop. Now we must calculate the distance x, right? Now to calculate the distance x, let's go. We can just use W net is equals to change in EK. Remember the hint, they made us to state the work energy theorem. That means it is best to just use the work energy theorem in calculation. But then looking at that, we can see that the only force that will be in D to C is only the frictional force. The only horizontal force that will be present is the frictional force, right? So we have work done by Fk, and then is equals to, breaking this down, this is half m Vf squared minus Vi squared. But then remember, we have the case of m here. We do not have the value of m. But remember, we are given the momentum, right? And then we already have the velocity. So the momentum was 5.79. And then we are looking for the mass now. The velocity, we calculated it, it's 3.86. Then we can just divide both sides by 3.86. Divide by 3.86. Then our mass is equals to 1.5 kg, right? So now we are done with that. We now have the mass. So, but what is work done by Fk? We can break this down to Fk delta x cos theta, right? And then this is half. Our mass now is 1.5, so substitute 1.5. But what is the velocity finally? Remember, this is the velocity at D, and then at D it comes to rest, so that's 0, and then square. Minus, what is the velocity at C? So the velocity at C is 3.86, the one we calculated previously. Then here we have Fk, we are given it's 3, and then we have delta x, and then cos 180. Why 180? We know frictional force is always opposing the motion of an object, therefore it is opposite to the displacement, right? Then having to calculate all this, it will give us negative 11.1747, and this here should give us negative 3 delta x, then is equal to negative 11.1747. Then we can just divide both sides by negative 3, and then we have our delta x is equals to 3.72 meters. Awesome. That's how we have it.